Right. Welcome back, Science 9. We are going to do a parts per million lesson and a little bit of reinforcement lesson regarding ppm and calculation of it. We are going to go through some of those other intermediate to a little bit tough examples today. So let's dive in. I need you to take a blank piece of paper and a calculator, something to write on, pencils to be precise. All right, let's go. Okay, first thing first, parts per million, ppm. M is represented by million, which is theoretically determined by 6 zeros, or sometimes using an exponent system, we used to put it 10 to the power 6. There are some other format of parts per million, which is known as ppb, B represented by 90, thus billion. Or if you go other unit, something that is more larger type of a unit, you can also think about parts per thousands. And some people, you may have already guessed it, it's 3 zeros, so it's 10 to the power 3. I wonder if you find a pattern from the exponent, because when you look at the parts per million as a middle ground of the whole spectrum, if you will, 3 extra 0 multiplication is happening for parts per billion, and 3 less, aka divided by 1000, is happening for parts per thousand. So we're going to do with some of those example questions that require parts per billion and parts per thousands. Right, so let's go with our first class example. As you can see, we have a scenario going on, so I will let you pause the video so that you can copy the context. Should take about a minute or so. Now, I assume that you guys copy the questions. I am going to highlight some of the key clue. First thing first, 0.025 gram of glucose that is dissolved in 2,000 kilogram. First thing first, you need to identify what these number clues representing. 0.025 gram is actually something that is dive into water in this case, I assume 2,000 kilogram of something. It didn't really say what solvent type it is. However, water is a universal solvent. It dissolves most of the material, so we can just hypothetically says that. So it's not a best problem I chose. But regardless, glucose is being dissolved. That's a fancy way of referring, or indirect way of referring, that this is a solute. On the other hand, 2,000 kilogram is my solvent. But now I want you to think about it. Let's think. 0.025 gram is really small amount compared to 2,000 kilogram. That's 2,000 ton. If I convert that in gram, that's 2 million gram. We can kind of estimate in a way that I don't need to necessarily add 2,000 kilogram with 0.025 gram, just because the differences will be very minimal. So we can kind of hypothetically assume that in this case, because solvent is really enormous amount, I can just directly go with the problem solving situation, assuming that this is equivalent as almost like a total volume or total mass. So let's put some of these into a formula. I'm going to do a traditional formula first. What I mean by that is this. I am going to put 0.025 gram on the top. At the bottom, I am going to put 2,000 kilogram. No, you gotta convert that into another one that has the same unit, in this case, which is gram. Gram and gram cancels each other. So instead of 2,000, I will put 2 million. Once that happens, you can multiply by 1,000. Remember, parts per million is you are comparing about 1,000,000 differences between solute and the solution. So once you get to that point, you can use your calculator. I'm going to use it over here. So you can use it. I cannot move back and forth, or I don't have time for editing about this one. Then multiply by million. Then you should have 0.0125 ppm. As you can see, the parts per million is really small value because, let's admit, 0.025 gram, that is such a small mass compared to 2,000 kilogram, which is the reason why this question also asks you about parts per billion. Some people really getting into panic mode and they say, Mr. Kim, I have zero clue what to do parts per billion. I never learned it. Think about it. Million and billion, what's the differences? As I mentioned in previous one, you got to do the same thing. 0.025 gram over 2 million gram in this case. Only thing is, instead of 10 to the power of 6, you add 3 more zeros, so that's 10 to the power of 9. Which means you will have 12.5 parts per billion. This should make sense to you because parts per million versus parts per billion. Parts per billion is the unit that people use when the distance between the or relative comparison. Solute is really even further away from the solution. So you even compare with 10 to the power of 9, 90 compared to the 60. So long story short, if you theoretically multiply this by 1,000, you will get parts per billion. In fact, if you multiply this by 1,000, you will get something called 12500 parts per trillion. And normally in grade 9, we don't go to trillion. So far, we learned about how we can punch the number in, solute amount, solution amount, and figure out the concentration using parts per million or parts per billion. Theoretically, we can even go parts per 1,000 or parts per trillion, which we don't need to go. It's just how many zeros that you're multiplying with. Sometimes you need to know the concentration, in this case parts per million or parts per billion, may be given by the question. So you need to go other way around. How can I find unknown value, which can be amount of solute or amount of solution? Whenever that happens, we need to set up an equation, x if you will. So I'll tell you a little bit. There are two different scenarios that you can think of. So first scenario is, let's say the concentration is given. So let's say 1.2 parts per million. Also, the solute is given. Let's say 5 grams of glucose as an example. Solute is given 5 grams. You don't even need to put what chemical type, to be fair. Then naturally, I need to find solution. You can define that as unknown x, because what you can do is then you know what goes on the top, you don't know what's at the bottom, multiply by million, that give you 1.2. It looks tricky, but now all I gotta do is isolate this x. On the other hand, some other cases, concentration may be given. Sorry, I'm just using hypothetical situation 1.2 parts per million. Solute, what is being dissolved, we may not know. That's very bad question mark that I put. X. Solution may be given to you. Let's say it's in 100 kilogram, something like that. Then you can apply that unknown on the top. At the bottom, you don't know what it is. And on the right side, you can get that it's in ppm. Some of you guys who sharpen up probably already figured out that I'm using the original formula that we just did in the previous one for the previous for this number one scenario, because everything is in gram. Although I didn't show it in this video yet, I can use my method, which is comparing milligram and kilogram directly, because, milli and kilo. If you think about milli to gram, there's 1,000 difference. Gram to kilogram, there's 1,000 difference. So if you pick milligram and kilogram, you don't need to multiply by million again like in previous one. So I personally prefer, whenever there's a unknown x situation, go ahead with the second method, which you will see that I'm gonna go with that method. So let's do this. Similar as before, I want you to pause this video so that you can copy the question. All right, I think you guys copied the question, assuming that the video will stop. Let me highlight a few things. So, number one, the question says total mass of solute. So we already identify which one is unknown variable, x if you will, in 1,500 gram of solution with the concentration of 5.2 ppm. So for me, this question can be really easy if I use milligram and kilogram situation. But because it's in gram and some people really like traditional method, I'll just do this question. Oh, actually, sorry. I used the traditional method before. I'll use my method, which is it requires a little bit of a unit conversion. As long as you put milligram of solutes on the top and a kilogram of the solution at the bottom, you don't need to multiply by million because that will give you whatever ppm directly, which is in this case 5.2. The only thing you need to be careful is solution, aka kilogram part at the bottom is given. You should not use it directly as 1,500 gram. So if I rewrite in a good way, you should put solute, I don't know, that's on the top, x on the top, and at the bottom, 1,500 gram, you gotta divide it by 1,000. So 1.5 is a kilogram at the bottom, which is equal to 5.2 ppm. So voila, you just figured that out, that x over 1.5 is equal to 5.2. Some people get intimidated by this unit. I can tell you this. Ignore the unit if you use my method. Only thing you gotta do is this. Isn't that looking familiar? This is like grade 8 and 9 math. You just need to deal with the one-step equation. What you need to do is x over 1.5 is a fancy way of saying x divided by 1.5. So you gotta multiply by 1.5 to get rid of my denominator that I don't want. So x is equal to 5.2 multiplied by 1.5, which is 7.8 milligram. If the question gives you 7.8 as a milligram or identify as a milligram, feel free. Right now we don't have anything necessarily said you have to use this unit. So original one was gram. So all I'm gonna do is just divide it by 1,000 to represent it as a gram. I will accept any of those above. Okay, we are at the last example. Similarly before, I want you to pause this video, pause it real time, because it look funny if you don't pause it. Pause it, copy the question, and then play again. Okay, so I assume you copy the question, so I am going to go with the highlighting identification step. The question says, determine the total amount of solution. That is a denominator that we need to find. If that much of chemical, in this case oxygen, milligram of oxygen, is dissolved, and then you got 0.12 parts per million. So what does that mean? That means I know which number to put it on the top because it's in milligram, and also oxygen says it's being dissolved. So in this case, the solution can be water or even air, theoretically. Total amount, we don't know. X, if you will. and that should be in kilogram. So we can find it in kilogram and then convert it accordingly. It didn't really say what amount unit that you need to use, so we can go afterward. That is equal to 0.12 parts per million as a unit. Like I said, if you're worried about the unit, you have a hard time dealing with it, then I'm okay you tentatively just putting the numbers only, as long as you can remember that top number belong for milligram, bottom number belong to kilogram. I'll tell you a little bit of math hack in here. You may know this a lot, you may know this already or may not know this. Do not copy this portion yet. I'm gonna use purple color. Theoretically, when you isolate, you gotta multiply by the bottom number. In this case, bottom number is the denominator. Then you may notice that it really didn't isolate, it really just moved x to the other place. And now unknown moved to the right side, so opposite of multiplication that I need to do is, well, divided by 0.12 on both sides. And you're canceling this numerical coefficient. This is really tricky way of undergoing isolation. So what I generally tell you, ladies and gentlemen, is if you have nothing but a fraction on the left side, and imagine, now you can write things down with me, the bottom denominator is already isolated as a single x, and on the right side you have nothing that is being added or subtracted, then you can switch this guy, do a good old switcheroo rule. It's a special case. In grade 9 you can luck out because a lot of formulas in science and math, more science, have an isolated fractions equal to whatever number situation. This may not occur a lot in grade 10 where you have a complex or more advanced algebra. But in any case, in this situation, 0.008 divided by 0.12 should be equal to x, and all you guys need to do is use a calculator for this one. 0.008 divided by 0.12 gives me, oh, it's nasty. The total amount is 0.0666, and it's actually repeating, kilogram, which is a perfect situation. I can just round it up using the gram. All I gotta do is from here to here multiply by 1,000, so it goes 66.7 gram. That's how you solve the problem. So that was today's lesson. What I put as a homework is a whiteboard question, which you can find in my Google class of Science 9. If I elaborate a little bit, instead of making scenario on everything, I just created some simple ones. Let's say the first step, listing step, is already done. You just need to find what's unknown. Like for example, the first question says 1.5 parts per million is a concentration. The total amount of whatever container is 200 kilogram. What will be my solute amount? I highly recommend my method where it says milligram is on the top and kilogram at the bottom, just because it will make your life easier. But if you really like, you know what, I like to compare everything by gram per gram and then it gives you ppm, parts per million. I'm not going to stop you. Just know that you got to divide million first algebraically to undergo with the others in order to make your life easier, even though that's not ultimately the only way that you can do, but I like to take a shortcut. That is a lesson for today.